Approaching assembly challenges. Almost there. But first we've got some more functions levels to complete. Let's take a look. X-Racer. Is this gonna teach me? Yeah, I think I've already checked this one out. This is supposed to teach me hexadecimal. Oh no, this is gonna be even more difficult than 2's complement. Especially under time pressure. Okay, shift sounds like multiplication. Division, wow, cool. And the lab. Okay, I think I've heard something about the lab. So let's start, I think let's start with the non-level levels. Let's start with Hex Racer and lab. And then we'll proceed with these, which I expect to be actual challenges. Let's take a look. Oh, no, you bastard. This level is my second favorite pastime. Converting hexadecimal to binary under time pressure. Okay, well, so hexadecimal can encode, yeah, 4 of my bits. Okay, well, let's just read. When dealing with a lot of bits, binary can become hard to read. Hexadecimal base 16 is even harder to read and represents each combination of 4 bits as it's shown as its own character. Yes, exactly. Cool. As an example where hexadecimal is much cleaner, let's compare the representation of the largest 16-bit number. Decimal 65535, yeah. Binary is 1,000,000 ones, and hexadecimal is... Okay, so I kind of... This is probably the only use of hexadecimal I am willing to accept, as well as probably 0x00, to what's the word? Signify a bunch of zeros, I guess. But anything other than F's and zeros is just impossible. But oh well. It is not easy to tell if the binary is missing a digit. I see. Or if the decimal number... Well, it's not possible to tell what the decimal number is at all, I would say. The hexadecimal, on the other hand, is immediately clear once you get used to the representation, at least. Well, everything's immediately clear once you get used to the representation. Toggle the bits in the level panel so they add up to the hexadecimal number in the question. You must beat level 3 to pass, and there's a mercy mode. Well, let's try it the hardcore way first. Let's start. 01, so 01, done. 02, 02, done. 03, it's just, oh no. See, this is my PC lagging. D, A, B, C, D. It's gonna be 13, I think. Oh no, what is 13? 13 is 8 plus 5. Was D 13? No, this is 11. What's 13? Yeah, D is 13. Okay. Okay, 1, done. 2, done. 3, done. 6, done. B is gonna be... Okay, I need to remember that whether A is 10 or 9. I think A is 10, right? A is 10. Let's double check. Yeah, A is 10. So from there I count up. So B is gonna be 11. Although it's kinda... I think it's probably better to start at 9. Yeah, so I start at 9, and then A is plus 1, B is plus 2, C is plus 3. Let's try again. 1, 2, 3. So C is plus 3, so 12. 1 again. Great. E is gonna be plus... Oh goodness, is it plus 5? 14. Yay. 6. 5. No problem. 2. No problem. 4. Sure. Oh no. 1. Well, this is just a 1 plus a 3. 1 F. 1 F is everything. Give me everything. Okay. See, this is my PC lagging. I'm sorry. can't do anything about it. I've tried for the longest time. So 1. E is... I've already forgotten. Okay. 0, 0. Submit. 7. I think I've done it. Yeah, I did it. 2 plus... No, this is not 2. This is 2 plus 6. A is 10. 10, 10, 10. 10 plus 2. Perfect. 2 plus 6. Let's keep going. As far as I can. E is this. 12. So 1 and 2. Submit. 2F. 2 and everything. Submit. 0, 7. Submit. 3, 9. Oh no. 3 plus 9. Okay, I'm getting... No, I was gonna say I'm getting decent at this, but I'm not really. Good job! I reached level 4. Timeout? Oh, I didn't... I'm pretty sure I submitted a correct answer to level 4. Wait. I thought I was already at level 5 or something. It felt like a million years. Okay, hexadecimal, toggle between signed, unsigned, and hex numbers. Sure. So is it gonna be up there? Proceeding with the lab. Welcome to the lab. Like the component factory, this is not a normal level, but a tool. I can't tell if I'm in a lab. Snow, well, it says it's the lab, but it doesn't look different. Oh, I do have this IO stuff. Sound. Hold. Wow. Okay. Welcome to the lab. Like the component factory, this is not a normal level, but a tool. Programming on buggy hardware is very frustrating. Oh, yes. It is painful to suddenly be forced to reason about circuits when you are in the middle of solving a programming problem. It is tempting to apply a quick fix, so you can get back to solving the original problem. But now this quick fix broke something else in the program that used to work and so on. Therefore, when developing hardware, try to aim for 100% reliability before you start programming. Well, I mean, I do, I think, try to aim for 100% reliability, but I think he's only just now going to introduce me to a way I can actually ensure my hardware is 100% reliable, because so far I've had no way to test it myself. This level uses programs to test your circuits. When the programs are run, this level checks if the linked components behaves the way you expect. The lab has 2 extra keywords. The expect keyword, so in here, or what? Expect, yeah. So expect is the same as const. It's a keyword. The expect keyword is used to describe what a value a memory address should hold next tick. The first number after expect is index of the linked component. The second number is the expected value. The linked component index is just the order the components are connected up to the program component. Well, this is an issue because I have huge components which are not, I think they're not even linked. Okay, let's take a look at this. Which state? I don't really understand what's up with the which state. I do have linked components, but I don't think I have my RAM in my stack linked to the program yet. I should do that. For example, expect 2, 4, copy 4, underscore. Would you look at that? They also use underscore for 0, I think. So we came up with that independently. Here the first line says that we expect the second link component to hold a value of 4 after the next tick. That's not particularly useful if I can only test a value in a register. Right? What's actually interesting is I would like to test a bunch of values on my stack or in my RAM. A register I can just look at, basically. I mean, I guess this is useful for automated testing and writing actual unit tests, but... Oh well. Okay, here the first line says we should expect the second link component to hold a value of 4 after the next tick. On link components are checked against expectations at every tick. All link components are expected to be 0 at the start of the program, and expectations for memory components only change as you specifically change the expectations. I see. The one exception are counters. These are naturally expected to increment each tick. The second special keyword for the lab is set input. I see. How about expect output? The second special keyword is set input. With this, you can control the input of the computer. Sure. You can at any time also re-import example tests by clicking below. I don't like clicking on Overture when looking at leg. I'm scared of losing my leg. Give me Overture. Okay. Overture. Oh. A bunch of tests, huh? Oh, I load it. I see. I load it into my program. So what does it look like? Expect 0, 1, 1. Register copy. Oh. S1, S2, S3, S4. Well, this is not readable. Oh, I see. So this loaded up. No, I don't see. I don't understand what the difference is between these tabs. Oh. So there is no difference. I see. So this is just a quick overview of my program tabs. Toggle expectations on off. Stack is unconnected. Okay, let me switch back to my leg. What am I supposed to do? Oh, well, I think I haven't read. Since you have now completed the leg, I have unlocked all the 16, 32, and 64-bit components that you have in the sandbox. Whoa. A 64-bit switch. A 64-bit register. A 64... Okay, how about a 64-bit RAM? Dual load RAM. RAM with an extra load pin. ROM. Read-only memory. Fast, but... Wait. Read-only memory? Save. Sandbox only. But... Well, in order for the ROM to be useful, I need to, at some point, hard-code it with some value. Do I... Oh, I guess I save to it in the sandbox and it stays that way? Okay, that, doesn't matter, this is not the point of this level. But what is? How do I complete this? Oh, I have completed it. Okay. And I unlocked... Yes, and I unlocked a bunch of new components, such as a keyboard, a display, a console. Wow. That's impressive, actually. Offset. Wait, but offset is not... So I assume the console will be printing... characters, ASCII or something, or is it just, yeah, it's text character display 80 by 24. So I understand the offset, but then I would also want to load the character into it at some point. Font page, Apple, APL. I think that's a programming language. Apple with insane notations. Okay, what else? File loader. Reads bytes from your hard disk. Which hard disk? My hard disk as in the hard disk of the computer the game is running on? Or is there a hard disk component? File not selected. I don't wanna. Keyboard. Key value, key up, key event. Oh. I think once I press this, yeah, I can now send key events to it. Cool. Okay. Oops. Well, this is all very interesting, but this is all entirely sandboxy. I don't have any levels with this. Dot matrix display, that's cool, except 6 by 8. Why is it 6 by 8? And can I wire under it? Yeah, it looks like wires. No, actually, I can't read. Oh, they kind of can. Yeah, so they can. You can run wires under this, and you can run wires under this. Yeah, and then you can connect them up like so. And this way you can have your display an arbitrary size, but you will have the ability to connect wires to them. Okay, enable X, enable Y, pixel flash. No idea how this works. This is interesting, but not for my current intentions. RAM. Latency RAM, oh no. This kind of RAM would add 1024 delay to the circuit, but instead of extending the duration of ticks, we simply don't wait for the output. This means that reading or writing takes 1 ticks. What? What is the delay of my circuit? Sandbox. Lab. Okay, so they are different things. Now I can see it. There's so much new stuff to explore. But I have no intention to build anything out of this yet. Okay, well, I guess let's leave it be. Let's proceed with actual levels. That will use, I assume, regular old components. Shift. To shift the value 1 left means moving all the bits in a byte to the left by 1 position. Shift left 1. Sure. This is multiplication by 1, or sorry, by 2. The task in this level is to shift the first input to the left by the value given in the second input. The second input will never exceed 7. Well, I'm not so sure about that. Okay, so this is my... I wonder why it's upside down like that, or rather lopsided. You know, usually you have stuff on the left and output on the right, but this is vertical. Okay. We do get all of our basic gates. So obviously shifting by 1 is no problem. But a problem is being efficient at shifting. Shifting by an arbitrary value. So is it enough for me to split once? And then maybe I can do something clever to decide how much I shift by? Or do I basically need the equivalent of a bunch of splitters all wired up differently? And then... Wait, but no, but splitters I cannot... Yeah, so I was thinking, you know, I could have... Yeah, no, so then I would also need a bunch of makers, something along these lines, you know. All of these would represent different shifts, and then I'd have however many switches, you know, something along these lines, among which I decide. This seems like a bit of a inexpensive and very direct solution. Perhaps there is some more elegant way to do this, but it is hard to see. Because once I have done, so let's imagine I have this, and once I've shifted by 1, I also need a way to decide whether I'm shifting by 1 or by 2. So, I mean, I guess something I could do is I could use the shift multiple times. I could chain these shifts, but that wouldn't save me anything, pretty much. Right? And that would only cost me more delay score. So, you know, one thing I could do is I could chain them like so, and then decide to proceed. Oops. To proceed or to jump out, you know, to the output. This is another way I could make this, but yeah, this will still need many of these components, which are free, to be fair. And the only thing that costs me is the switches or the muxes. Yeah, but this will increase my delay score because it will chain all the muxes together as opposed to deciding in parallel. Okay, any better ideas? I think I'll take a quick timeout. And if I come up with anything, I'll be back. Nah, I don't think I'm gonna come up with anything better than my very first idea of doing something along these lines. So, another thing I haven't considered is the possibility of using some gates for this. But I don't think any gate is gonna be able to help me here because I need to shift by 1, and how much I shift this bit does not really depend on anything else in the original byte, right? So if I need to shift a 1 by 4 or whatever, it doesn't matter to me what the value of 2 is. Which means I can't really combine this one with anything using any gate. So, and there's a bunch of course, there's a bunch of ways to wire this up. Like I said, one way is this. Another way would be something, you know, chained, where each step is a shift by 1, and we have up to 7 shifts, up to 7 steps. Or it could be even done even in an even more crazy way. I could, for example, create a byte. So this makes no sense to actually use, but I could create a byte of. Nah, I'm not even gonna go into the explanation of it. So yeah, I will implement it this way with 7. Although, can I have a 0 as my input? Yeah, I think I should also be able to handle a shift by 0. So I will have 8 of these, and I will decide between them using probably decoder board or something along those lines. We'll see how it goes, but first I'll implement the 8 and I'll be back. Actually, now that I'm starting to look at this in this shape, so right, I've started implementing shift by 1, shift by 2, shift by 3. I think it might be more efficient to use singular switches as opposed to these 8-bit switches. Although, I mean, well, yeah, in terms of gate score, it should probably be better. So my original idea was, of course, to attach switches everywhere, like so, and then decide. But when you look at these, the more you shift, the more bits become irrelevant. And if the bits are irrelevant, then you don't need to switch them. And so it's going to be wasteful to be switching this and this and this and this with my 8-bit switch, as opposed to just putting something like, you know, this. Well, it doesn't fit. Oh, that's going to be huge. Oh well. But you get the idea, right? So I should probably aim for that instead. Yeah. Even if it's expensive in terms of space, I'm not rated on how much space my component uses. So I'll probably try to go with the singular switches. Okay. I'll be back. Okay, this is something I came up with. This is not yet final. This will not work, of course. I'll explain why in case it's not clear. But first of all, well, I decided it would be probably a good idea to not shift wires, but rather shift inputs and outputs, right? So my inputs remain the same, and I just shift the output up by 1 every time. This is not exactly easy to read, I guess. It may be easier if I shift all these down by 1, like so. But then you get mess with wires in here, which is why they're shifted 1 up. Oh, okay. This is good. So yeah, this is my original idea, but this kind of, I'm not sure what it is exactly, but the shifting of the outputs relative to the inputs somehow makes me feel intuitively like there is something to be optimized here. Almost as if somehow I could just have a single switchboard leading to a bunch of different 8-bit makers somehow. But I can't really place it. I don't. This is probably just a weird and not correct intuition. So yeah, this is, like I said, this is not going to work actually, because while we switch these singular bits, as soon as they get piped into the maker, they stop being switched basically. And this is going to be an output of 0, and we are going to have a short circuit if we just connect them up like so. Which actually means that we will have to bring all the ones together. Oops. We'll have to bring, so this, and this will have to be connected before getting piped into a bit maker. You know, like this, and then this gets piped into a single output 8-bit maker. And so on for the second, for the third, and for all the bits. So I'll do that. I'll probably color them so it's a bit clearer. Do I even have 8 colors? Yeah, I have 9. Okay, so I'll probably use a million colors to distinguish which is which, although we'll see. So next time you see me, expect a huge connection circuit grid thing to the right, leading into a single 8-bit maker. Oh, I've just realized I wired it up completely wrong. I connected all the ones to a single wire. So this is an incredibly convoluted way to take a byte, split it, and make the same byte. Yeah, I don't need to connect the ones to each other. I need to connect the output positions that correspond to ones to each other. So let's get rid of all this. Oh, that pains me to do, but it has to be done. So let's take a look. Again, what I have is I have 8-bit makers, but they are shifted like so, right? And then they're just stacked on top of each other. So really, I don't... oh, actually, one other thing I forgot. Completely forgot one other thing. Is I still need a one-to-one thing. You know, like this. Kind of. Except... okay, I'll fiddle with that later. But for now, let's not bother with the one-to-one. Let's first consider exactly how am I going to get rid of these 8-bit makers. So my 2 is going to be either this or this or this. Aha, so... this is awkward because, right, I only have basically one where it matters. It will be here. And I have only 2 2s where it matters. But then 128 matters the most. Well, that, I guess that makes sense. So let's start with 128. So I want to connect this and this and this and this and this and this. So wait, did I connect it correctly? This is actually, this is so confusing. I am connecting the lowest. Yeah, no, I didn't. So I need to start from the bottom. That's actually, again, an interesting thing that intuitively feels like it should be reducible. But well, I'll first I'll build it and then we can see. So yeah, I'm starting from the bottom. Instead of starting from connecting all the ones, I need to first connect all the 128s, then the 64s, and so on and so forth. So be right back. Right, this should be correct. I'm not particularly happy with this. It's definitely an insane mash of colors, but that's not really the issue. Still seems like something could be improved here. But I can't really understand what. I mean, I could remove all these splitters, of course. And I could have a, you know, another grid here. But I think with splitters it's probably a bit easier to read. That said, I still need to decide which switches to enable, right? I had it connected up vertically like so, but that was obviously wrong. I need to set a decoder, I think. Although we know that this 3-bit decoder is a little bit wasteful because of the enable pin. But oh well. Yeah, and based on that, I can decide whether it's 0 through 8. So yeah, I think I'd rather use the decoder still. And how am I gonna wire it? I'm just thinking, where do I want to bring out the red wire? But yeah, so we'll have this is my shift input 2, right? Shift by, yeah. So shift by is gonna be piped into a decoder like so. Should be no problem. Something along these lines. And then I think you know, something along these lines. And then if we're shifting by 0, so this goes all the way up, versus the maximum shift is this, and this is going to be down here. So would I perhaps want to put it, I probably want to put it up top. I don't know. I'm not sure. Yeah, this is still gonna be crisscrossed. Maybe I could put it over here. And then it's not crisscrossed, right? Then it's gonna run fairly nicely. Okay, okay. Can I bring these out? Yeah. Oh, that's actually perfect. Okay. And I bring the red cables out there. Okay, okay. So, be right back. Alright. Guess I'm calling this solution Mark 1. Let's try and test it. Shift the bits of 251, left by 0. 251? No problem. 20, left by 6. Wow, that's a lot. I'm getting a 0. Is that correct? I think that should be. Yeah. 20 times 2 to the power of 6 is 1,000,000. That doesn't fit. That's going to overflow. Yeah. Looks like it's working. Cool. Do I get a component for this? In addition to giving you a shift left component, we also had to in turn create a shift right component. Sure, no problem. All we had to do was to create the mirror version of this schematic. No problem. I recommend that you add a shift left and shift right to your hardware for future levels. As into my... Oh. I thought he meant to the lab. Okay, so we have a gate score of 51 and a delay score of 8. Which the delay score of 8 comes from here. Huh. Wait. Wait, why is my delay score 8? No, the delay score of 8 does not come from here. What's the decoder delay? Yeah, the decoder delay is 6. So we have a large delay on the decoder. And then it just adds to the switch. A single switch. These are all parallel, they're not chained. Okay. Is there an improvement to this I could make? I do wonder. Well, I've been wondering this for the longest time now. And I still don't see it. It feels wrong for some reason. But I think I'll go with this. Anyways. Yeah. Sure. Let's just use that. Maybe if I come up with a better idea later, I can go back and optimize it, as always, of course. But let's proceed with the product of nibbles. What's up with nibbles? Do I need to multiply? Multiplying two 4-bit numbers gives you an 8-bit number. Build a circuit that does this. Oof. Multiplying two 4-bit numbers give me... Oh, I guess it does. Wait. This sounds like a very difficult level. Also, I don't understand why they're now all vertical. I don't really like this. Don't care. Okay. I mean, no ideas so far. 0. Do I need to go to the drawing board and try to multiply a bunch of numbers and see how it even works? Or what? Well, let's try and... Okay. So, I guess let's try multiplying 2 by 3 or something. 2 times 3 equals... What is it? What's 2 times 3? So that'll be... My input is gonna be 2 times 3 And the output needs to be... Give me a byte maker. The output needs to be 6. No, multiplying by 2 is too easy. Let's try multiplying by something more interesting. Let's try multiplying by 5. So 5 times 3 is going to be 15. So 5. Let's set this to 5. So 4, right? Plus 1. This is a 5. Times 3 equals 15. So, and 15, oh, 15 is actually everything. Wow, this is gonna be interesting. I think I might need to do, what's it called? Long multiplication or something? So I might have to write, 5, 0, 1, 0, 1 times 3. It's gonna be 0, 0, 1, 1. Right, and then I haven't done this in so long. So how do I even do this? 1 times 1? How do I do long multiplication in binary? Is it 1 times 1 is 1? But there's no carrying. I would like to carry 1 times 1. Wait, it's not okay, I'm really gonna embarrass myself here. How do I multiply two numbers? I mean, it's really, it would be 1 times 11 plus 0 times 11 plus this 1 times 11. So, and this 1 times 11 is 11 shifted by 2 zeros, because, yeah, so it's not actually, it's not, okay, so this is kind of how long multiplication would work in decimal, I think. I haven't done long multiplication in decimal in a million years, but I think what I'm really doing is, so basically, let's try and write this out differently. Yeah, that'd probably be easier to see. So 0, 1, 0, 1 times 0, 0, 1, 1 is gonna be, so we're gonna have 0, 1, 0, 1 is basically 0, 1, 0, 0 plus, or yeah, plus 0, 0, 0, 1 times this stuff, 0, 0, oh goodness, 0, 0, 1, 1, right? And because these are powers of 2, I just shift it by the respective powers of 2. So I think I could potentially do this in 4 shifts or something. But man, is this even how long multiplication works? I think it is. This is the idea behind it, at least. So yeah, this will be, 1, 1 shift by 2. Or is it by 3? It's by 2, right? Plus 1, 1 shift by 0. Right, shift. So we'll have 1, 1, 0, 0 plus 1, 1. Well, yeah, 1, 1 equals 1, 1, 1, 1. Yeah, that's what we have. So yeah, I think this is probably the way I would do it. Seems reasonable. So I would have, let's see, I would have This does seem wasteful though, right? Because I have an 8-bit shift. It's a major shift operation. Wow, they rotate right. There's also rotation. I also got rotation, not just shifts. Okay, but I don't need rotation now. I only need shifts and I only need shift left. Right, so I would have pretty much. So do I literally implement this right now? Yeah, I think I can implement it right now by using 4 adders, but this seems inefficient. Very much so, but I think at least this will work. So yeah, I want 4 shift lefts. Yeah, and three adders it's gonna be, right? Yeah. It's gonna be 4 shift lefts. I want some constants. Give me my constants. Yeah, and I shift left by 0. I shift by 1, by 3, or by 2, and by 3. So this will be 1, 2, 3. Constants are free, so I feel fine using a constant everywhere. Right, and then I would want to gather this into a byte. Let me disable all these bits. Again, just to reiterate, this is not my final solution, but this is something that would work, I think. Let's patch them up just the way I like it. Can even be compressed further. Okay, yeah, something like this. Wait, no, wait. Oh, actually, yes, this is correct. And then I'm gonna have 3 adders. Give me my adders. So I'll add these 2, I'll add these 2, and I'll add these 2. But these adders need to be... Oh, no. Wait, yes? Wait, no? Wait. Ooh, this is complicated because, see, it's not so easy for me to decide which adder to enable versus disable. So what I was thinking originally is just pipe this into the adder and then add it all up. Right, add it all up. Like so. This is gonna be my input to the adder. Add it all chained. And then have this output. But this is an issue because this adds everything up and I need control flow based on these guys. Oh, which actually, I can just use the fact that 0 is neutral under addition, so a switch is fine, right? I can just add switches here. So yeah, 1, 2, 3, 4 switches like so. And then let me space these adders out so it's neat. Yeah. I don't know. I shouldn't be doing this. So carry out. I don't care about carry. Do I? No, I don't think I care about carry because I shouldn't have any carries. Should I? Yeah, no, it's fine because these numbers will fit into a bit, so there no carrying is possible here. Okay. Yeah, and then just yeah, I shift by 0 if this is on. I shift by 1 if this is on. So let's make a grid. Let's make a grid like so. Wow, look at that, perfect spacing. And let's just connect this quickly. And that's my circuit, I think. I think this is my circuit. It's not efficient. I think it's very inefficient. I use a lot of different shifts, and I use these full adders even though I'm only adding small things. But this should theoretically work. Let's test. Okay. Yeah! Haha! Right, first try. And I get a Steam achievement for this. Complete the product of nibbles using no more than 3 8-bit adders, I assume. Yeah, I think I've even seen... Oh, I've even seen this one. I used 3 8-bit adders. Okay. Is this... So I think I saved on the number of adders by using these switches, because you could probably do something more convoluted. If you could have more adders here, and you could decide which adders you enable based on which shifts are relevant. But no, that seems even less natural than what I did, so I don't know. Okay, what you did here was actually multiplying two 4-bit numbers. Well, yes. We had the intern scale it up to bytes instead. No, I disagree. I object. I do not want the intern scaling this up because I am not sure how I would do it for more bits. Especially considering the carrying issues here. Although I guess... No, I don't understand. I really don't. Is it really easy to scale this up to a byte? So I would have, I mean, I would just scale this up, right? I would have more of them, right? This would be 4, 5, 6, 7. And then I'd have a bunch of adders. You know, it's actually gonna be however many more. I think I might need another one down below. It's gonna be 7 adders. And yeah, the only question is what's gonna happen with carrying. If I shift it, so say I am multiplying something large, like a, you know, 255. And say I'm multiplying 255 by 2. Well, the overflow already happens when I shift. So do I just pipe... Would I just pipe the carry into carry? Carry in, carry out? Would that be fine? Or does it not even matter? Do I overflow without worrying about carries? Yeah, I think I don't care about these carries. I think the carry on the 8-bit adder is only relevant if I am adding something like a 16-bit number. So if I'm adding two 16-bit numbers, I would want to use 2 adders, right? And then I would want to carry between them, just like I do with you know, the 8-bit adder built out of 2-bit adders. Yeah. So I think this is fine, and it's fine that we overflow, because overflowing is expected. Okay, sure. So I'll clean this up slightly, and I'll be back. Okay, just compacted it slightly. So like I said, I think I would optimize this by using smaller components, smaller adders and smaller switches and smaller everything. But since the intern did it for us and built an 8-bit version of this, I think an 8-bit version of this might require full adders. And I think that might be an efficient solution. Maybe not the most efficient solution, but I would be fine using this, I think. Seems okay. So I'm not gonna optimize this. Long story short, I wonder how the score is calculated for things that are shifted, things that are scaled up. Because it's really a non-trivial task, isn't it? You can't just multiply this score by 2 because using 2 of these won't be enough, right? If I do another one, I will still need to add their outputs, right? So we'd need another adder. And to figure this out based on my current... Okay, I cannot delete anything again. That's a weird bug this game has sometimes. Yeah, to figure out my score based on my current schematic seems like too difficult a task. I don't think this is gonna be extrapolated with any sort of precision. So I do wonder how it's calculated. Let's see how much a multiplier costs now. Math. Multiply. Yeah, so it was just doubled. I had a gate score of 500 and now I have a gate score of 1000. But the delay is still the same, which is actually weird because my adders were chained and I would expect the delay score to grow considerably actually. But it didn't. It stayed at 250. Multiply. Yeah, that's weird. Okay. Integer divide two numbers to find the quotient. A quotient? Quotient? No, quotient. I don't know how to read the word. And the remainder. Consider the fraction 7 divided by 3. 3 goes into 7 2 times and 1 is left over. Sure. So basically implement div mod. Here 2 is called the quotient and 1 is called the remainder. In this exercise you are first given the numerator 7 in the example and then the denominator 3. And you are then expected to output the quotient and then the remainder 1. Okay, so it looks like they're suggesting that division is not done using a hardware component, but rather division is a derivative of multiplication that is programmatic. Guess? Right, I'm supposed to implement this in assembly now? But wait a minute. Before I can do anything here, I will first need to modify my leg in order to include multiplication in my ALU. Ow. That hurts. Also, I think we've figured out that this mux structure is inefficient, so I would like to optimize that as well. Okay. Do I even do this now or do I leave it for the next video? Because the video is kind of long enough. Though it would be nice to finish functions today. Future me speaking into the microphone. My initial answer was yes, and I went ahead and tried to finish this level and work on the ALU, but nah, it's taking too long. I don't have that much time, and I'm afraid I'm gonna have to put that in the next video, so that'll be it for me for now. We're pretty close.